Thanks, Nicholas, and thanks everyone for waiting for so long. I'm Shraddha Singh. I'm a PhD student at Yale University with Steve Girvin and Shruti Puri. Today, I'm going to be talking about the work I've been doing with Steve Girvin and Baptiste, who was a postdoc of Steve until 2021 and now is an assistant professor at University of Sherbrooke. Before going forward, I'd like to thank the organizers of the conference for giving us a chance to some of us to escape the harsh weathers of Northern Hemisphere. All right, so the motivation behind this work is a hybrid oscillator qubit architecture. Essentially, we'd like to see the most optimal approach towards scaling up superconducting qubit technologies with all the components that have been given to us. On my right, you see, not on my right, actually both of these are on my right, but on the right side of the screen, you see the multi-level oscillator, superconducting oscillators. So oscillators are multi-level systems, which are rather long-lived. For example, the best bare lifetime that you can get is a second, but they're much harder to control. That is, it's harder to do gates on these systems. Then on the right, you have the two-level systems, which are your transmons or fluxoniums, for those who are familiar with it. These are two-level systems, which are rather shorter-lived compared to the oscillators, but have faster control. An average single qubit gate error rate stands at 10 to the minus 4. OK, so the idea is to find an amalgamation, a perfect amalgamation, where I use the best of both worlds from these two components. I'm going to use my oscillator as a memory, while I use the two-level system to gain access to this memory to just do gates. And that's going to be my hybrid oscillator qubit architecture. Now, these oscillators, being multi-level systems, can be encoded to have better lifetimes. And the state-of-the-art oscillator encoding was demonstrated to be the GKP qubit, so I'm going to be using that for this talk. All right, so far, we've used this hybrid oscillator qubit architecture to improve the lifetime of the oscillator already by a factor of 2.3. And the T average quoted here is actually the oscillator lifetime used in this experiment. The goal of this work is to extend this result further into accessing universal control of these logical qubits using the two-level ancilla. OK, so here's the outline. I'm going to first review the oscillator encoding, the GKP states. Then I'm going to talk about a framework that I've been developing with Steve, the non-abelian QSP, which has really good applications to GKP states. And I'm going to be talking about one of them, that is the measurement-free gate teleportation, which in some sense is an error-corrected gate teleportation for these qubits, much like the lattice surgery, if I can code that. OK. Before we begin, I'm going to start with some basics of the oscillators. So I've shown you these multi-level systems. Errors in these systems could take you one level up or one level down. These levels represent the number of photons in these states. So the one state has one photon, the two state has two photons, and so on. You lose a photon, you go one level down. You gain a photon, you go one level up. Those could be your errors from the environment. There is an alternative representation of these oscillators where I can assign a position and a momentum to each of to the oscillator, and thus you have a phase space where the position of the oscillator can be changed by traversing along position axis, and the momentum of the oscillator can be changed by traversing along the momentum. This D operator is called the displacement operator, which just takes real arguments to traverse along the position, imaginary arguments to traverse along the momentum. Now, position and momentum operators do not commute for a quantum system. And so these displacements do not commute either. And the reason behind that is that these displacement operators are just exponentiated position and momentum operators. There's a very intuitive way to understand this. If you're traversing along the position, you're not disturbing the momentum. So the displacement along position would be something that commutes with momentum. So it should be a function of the momentum operator, and that's just the exponentiated momentum. Same goes for the momentum boost, changing the momentum. Now, I'm going to be using a very special hybrid gate in this work, and that's the conditional displacement. Oh, I forgot to mention this. So the group commutator of these displacement operators depends on the area captured by these vectors. That's one important thing to know, to keep in the back of your head. Now, I'm going to be using this very special hybrid gate, the conditional displacement gate. What it does is, it displaces your state, your oscillator state, conditioned on your qubit state. So for example, I have this blue dot, which represents a state at the phase space origin at x equals 0, p equals 0 mark. If I apply this conditional displacement gate with the qubit in, say, G or E state, I'll move to the left if I were in the E state, to the right if I were in the G state by alpha. If I were in the plus state, I will end up in an entangled hybrid oscillator qubit state. Now, in order to control my oscillator, I will define an instruction set. There are several instruction sets available to access control using a two-level ancilla, access control of the oscillator using a two-level ancilla. I'm going to be using a very specific one that requires conditional displacements, because those are favorable for GKP states. So my instruction set contains arbitrary qubit rotations, single qubit rotations for the two-level system, conditional displacements, which can also be seen as a momentum-dependent rotation of the qubit, then conditional momentum boost, which can be seen as a position-dependent rotation of the qubit. I'm going to be using this position-dependent rotation and momentum-dependent rotation jargon a lot throughout this talk, instead of calling them conditional displacements and conditional momentum boosts. This instruction set was demonstrated to have universal control of the oscillators in this nice paper by Alec Eichbusch, which was released in 2022. And we're just extending all of these results further by getting some analytical framework to explain their results, their experimental results. Now, let's go to the GKP code framework. This was founded by Daniel Gottesman, Alexei-Kitaev, and John Preskill in 2001. The encoding essentially is the following. The zero logical state is a superposition of states located at even multiples of root pi in the position axis for the oscillator. The one logical state is a superposition of states located at the odd multiples of root pi. That defines your 0-1 basis. Your plus-minus basis is defined in the momentum basis. So given you have even multiples of root pi as your momentum, the superposition of those states would be your plus logical state. The minus logical would be, similarly, the odd multiples of root pi momentum values. So now I've defined my 0-1 basis and the plus-minus basis. The point is, how do we gain information of these continuous variable states using two-level ancillas? The thing is that these 0-1 logical states contain bitwise information, and my two-level system can access these should be able to access these bitwise information using just one gate. And the gate I'm going to use here would be, OK, I'm going to be using this picture a lot, so let me explain this first. Here, the green arrows denote just one single qubit. The arrows are pointing in the same direction right now because the qubit is in a product state with the oscillator. This is just indicating the spin polarization of the qubit corresponding to each position eigenstate or momentum eigenstate given you're in the 0-1 basis or the plus-minus basis. So now if I apply this momentum-dependent rotation, I would have rotated the qubit entangled with the zero logical state by 2 pi, and I would have rotated the qubit entangled with the 1 logical state by pi, and thus I've entangled the two-level system with the 0-1 basis of the logical GKP state. Similarly, for the plus-minus state, I will apply this following momentum-dependent rotation, and I've entangled the plus-minus basis also. However, the problem is not solved because I don't have these delta functions I've been showing you. My oscillator cannot have specific momentum and position values, essentially because of the Heisenberg's uncertainty principle. If I have delta functions, then I would need to have the infinite phase space expanse. But I don't have access to it. In a real system, you can only have limited access in phase space. And In that case, your oscillator will have a specific position or momentum with some uncertainty defined by delta here. So the real GKP code words, again defined by Gottesman-Kitaev-Preskill, are going to be defined by this Gaussian envelope applied to these states, which basically increase the uncertainty in each of these peaks given this delta value. So now, whatever I told you for the entanglement of the two-level system with the GKP qubit doesn't hold efficiently. What happens is the following. If I now take a qubit, let's take one peak from the one logical state and study what this position-dependent rotation would do. If I apply this position-dependent rotation, for the delta function, yes, I will rotate by pi. But for the Gaussian wave packet, I will rotate exactly by pi at the peak, but everywhere else, I would have either under-rotated or over-rotated. To the right, I've rotated slightly more than pi. To the left, I've rotated slightly less than pi. And this is an error. This is an erroneous rotation, which will be mapped to the GKP entanglement, GKP qubit, GKP ancilla entanglement also. And thus, my entanglement efficiency is affected. And this is one crucial feature of GKP states, that we cannot access this bitwise information with a single shot, essentially because of this Gaussian uncertainty. And I'll show you how we can do that with very few conditional displacements in the next few slides. So essentially here, what we have is rotation errors on the qubit of the two-level system due to Gaussian uncertainty in the multi-level system. And this is where quantum signal processing comes into picture. So quantum signal processing, in very simple terms, gives you a desired rotation, given you have access to some erroneous rotation. For example, you want this erroneous rotation could be an effect of some hardware drive errors or some faults in your hardware. You don't have access to epsilon. You know what theta you want, and you have access to theta epsilon. And somehow you want to cancel this erroneous rotation. So what QSP does is it gives you the most optimal pulse in the form of additional qubit rotations to cancel this error without even the knowledge of epsilon. So if there was no error, that is epsilon was 0, these additional rotations would just give you identity operation. If epsilon was non-zero, then it would apply an effective minus epsilon rotation along the same axis phi. So here, my theta variable is classical, and my epsilon are basically errors due to classical amplifiers, classical faults. What I want is now theta to be represented by position and momentum, which are non-commuting variables. So now, my errors here would be due to the quantum uncertainty of the oscillator states, and thus the name non-abelian quantum signal processing. So I'm going to be using conditional displacements and conditional momentum boosts to correct for those rotation errors that you saw previously. Okay, let's see an example of how this would work. So I have this starting product state. The alpha equals 0 peak is representing my zero logical state, and the alpha equals root pi peak is representing my 1 logical state. Currently, I'm in a product state. My qubit spin polarization is pointing in the plus C direction, no matter which eigenstate you pick from here. Now, what I want is the following entangled state. That is, my qubit points in the plus C direction when it's entangled to the 0 logical state, and if it's entangled to the 1 logical state, it should point in the minus C direction. Initially, I told you to do something like this position-dependent rotation, which would rotate the qubit by 2 pi and pi, given you're at 0 or root pi. But that seemed to give you an error, which is proportional to x minus alpha. OK, now I'm going to tell you that this opening of the spin polarization that you see can be canceled by a momentum-dependent rotation, which makes the spin polarization basically squeeze in like that, and effectively cancels these errors. I'll show you why I'll show you the intuition behind this solution. So basically, your momentum operator in the position representation is a derivative operator. So if you apply it to apply exponentiated momentum operator onto a state with Gaussian probability distribution, what you get is the following. So I've only expanded the exponential momentum operator up to the first order because I'm assuming beta is small. So I've gotten a term which is basically identity, and the second term is obtained from the first derivative of the Gaussian operator. All right. So this second term is proportional to x minus alpha, and my error is also proportional to x minus alpha. Let's see how I can use this to actually correct the error that I just showed you. What I'm applying is a pre-correction, that is exponentiated momentum displacement tensor sigma y. This is the hybrid operation I've asked you to apply. And this would expand to first order as follows. Now, this still doesn't look like a rotation because there's no I on the second term. But so this is a very state-dependent argument. If I write sigma y as I sigma x sigma z on G, which is the 0 state of your qubit, is just G, then I can write this equation as follows, which is basically going to give you the exact rotation that you're required for canceling the error in the previous state. So the idea is you first apply that momentum dependent rotation on your oscillator qubit state. Then you apply this position dependent rotation, which decides the rotation according to the peak of the Gaussians. And finally, you will get the entangled state that is required. To appreciate how good non-abelian quantum signal processing is, I will give you I will tell you how many conditional displacements or momentum boosts I would have required if I were just using conditional displacements or just conditional momentum boosts. So it's not non-abelian, it's just continuous variable quantum signal processing, where theta can just be a function of x or just be a function of p. In that case, I can use the most optimal pulse that they have in QSP right now for 90-degree rotations. That's called BB190. And it would have required 7 times the length of the pulses that I'm applying right now, compared to the small conditional displacement or the momentum boost rotation that I am applying here. I call it small because my pointer is not working. Because the square root pi delta square term is rather small because delta is going to be small. OK, so I've given you a technique to entangle your GKP states with 2-level ancillas with high efficiency. With this entangling gadget, where you first apply a correction, then which corrects for the Gaussian, which applies a pre-correction for the Gaussian uncertainty, and then you apply the target unitary to rotate according to the peak values of your GKP state. These thetas and epsilons are decided as follows, given the previous derivation I just showed you. And then you can apply an unentangling gadget also, given you have an entangled state, by just applying the inverse of the entangling gadget. This is rather trivial. But you also have another option, which is basically applying a theta tilde for your unentangling gadget, which essentially comes from the fact that if you put this unentangling and entangling gadget, these unentangling and entangling gadgets together, you should have rotated your qubit by a multiple of 2 pi, because 2 pi is a period of rotation. This is allowed. And so instead of applying the inverse of entangling gadget, you could apply this theta tilde also. And this specific option actually has advantages in error-corrected gate teleportation. This is exactly the reason why we're able to do error-corrected gate teleportation. So now we'll be discussing the applications to GKP states. We found several use cases to GKP, not only just GKP states, but various oscillator states and oscillator control. But I'll be discussing these 3 specific cases for GKP states for this talk due to the time constraint. In the GKP literature, these 2 circuits were already available to us, the GKP logical readout and the small big small protocol, which is the stabilization protocol. The GKP logical readout protocol was actually a finite energy GKP protocol, where epsilon was numerically optimized. And our non-abelian QSP framework actually gives the analytical value of epsilon, which was exactly equal to the optimal epsilon founded by these numerics. The small big small protocol was founded by a dissipation engineering-based derivation. And this can be broken down into being composed of the entangling gadget and the unentangling gadget. So it's in some way applying a logical identity on your states, on your GKP state. So only if you have a GKP state, you'll be applying identity and doing nothing. But if it was something else, you will be applying autonomous error correction on it. So this non-abelian QSP sort of framework sort of ties up all of these circuits together. Now, the final part of this talk, measurement-free gate teleportation. So I'm going to show you a very trivial gate teleportation here. I already told you that we had the finite energy GKP logical readout circuit. We could have just applied the entangling gadget, applied a single qubit rotation, and then applied the unentangling gadget, which is the inverse of this entangling gadget, which would be equal to applying this circuit to apply a gate on your top qubit via your bottom qubit. Now, this other scheme which we found, because of the extra option of not having to apply inverse entangling operation for unentangling your qubit, which is the following. Here, my unentangling gadget is not equal to the inverse of the entangling gadget. And that, in fact, this entangling and unentangling gadget, if you put them together, these would give you, they would give you the stabilization technique that the stabilization circuit that I showed you on the previous slides. So essentially, this corresponds to having gate teleportation plus error correction on the top qubit. And I'm going to show you how, using essentially this argument, I will be able to mitigate ancilla errors during this during this gate teleportation scheme. OK, so let's review how universality can be achieved. I can achieve logical z theta gate as follows. You've entangled your GKP qubit with the two-level system. You apply single qubit operation, so that's applied, giving you a phase in the hybrid state. And then you apply the unentangling gadget, so your G has been pulled out. So basically, with the 0 logical state, you've rotated your qubit by 2 pi. With the 1 logical state, you've rotated the E by pi, and you've got G out in the end. And so your phase theta has been transferred to the GKP qubit now. So that's your logical z theta gate. For the logical x theta gate, I would use a circuit which corresponds to the following, to applying the following circuit, where the control is basically on the plus-minus basis. And that just corresponds to having the entangling and unentangling gadget in for the plus-minus basis of the GKP state. Finally, the efficiency of these circuits is as follows. The success chance of this scheme giving you a gate teleportation is 99.88%. It's not 100% because the QSP scheme that I showed you has some second-order terms that I ignored, and that leads to this small error. And the state fidelity that you get after this gate teleportation is 0.994, which is really good. And all of this in the absence of error, by the way. This is important because even in the absence of error, we did not really have a good enough circuit to do very efficient gates on GKP circuits. And this is very close to exact GKP gates. In fact, this is the only scheme that reaches these success chances and state fidelities for GKP states in the absence of errors. And you can generalize these circuits to only apply our x theta type rotations if, in case, for your ancilla qubit, x theta was easier to do than z theta, et cetera, et cetera. Finally, let's come to the problem. Let's visit the problem at hand, the ancilla errors. Now, if you're using an auxiliary system to do something to your main qubit system or wherever your code word is located, there are chances that errors from this auxiliary system could go into the main qubit space and corrupt the system. So basically, that's why we generally avoid using auxiliary systems. However, if you could protect yourself from one specific axis on the block sphere, on the ancilla block sphere, then you could use bias noise ancillas to make these auxiliary qubit-based protocols fault tolerant. In this case, it's not so. I'm actually affected by sigma x, y, z errors as if they would induce logical errors on my system. So I will show you in the next few slides how I can mitigate the effect of sigma x errors using the idea that this is an error-corrected gate teleportation circuit. So essentially, if you have a sigma x error, that commutes through to give a minus theta gate instead of theta gate. And that gives you a minus 2 theta rotation error. If I were to break this circuit down into m pieces, and I'm allowed to do so because my top qubit is being corrected during this gate teleportation, I would, in one instance of a single x, in a single x error instance, I would transfer only an error of minus 2 theta over m instead. However, at the same time, I've increased the probability with which I can have x errors. So this is some sort of random walk where the expected rotation at the end of the circuit, at the end of these m pieces would be as follows, given you know px. And the variance in that would, in this value would basically increase as m. So here I've done a simulation which shows that I'm able to beat the I'm able to beat the increase in the probability of errors by the decrease in the infidelity that is avoided by this increase in m. Okay, so what I do here is I'm running this circuit as if the control x gate here was not instantaneous, and I could have sigma x errors during this gate. The orange line here is the reference point at which, at m equals 1, as if you would have done gate teleportation in just one round. And the blue dots are the simulations, while the green one is basically the analytical form, which I checked. So the analytical form matches, and the blue dots basically show you the decrease in infidelity that you see as you increase m. If you zoom in, if you increase the m's, you can see that it keeps on decreasing. It doesn't saturate at a specific m. It doesn't start increasing after a specific m. It keeps on decreasing. So you're always decreasing in the infidelity faster than the increase in the probability of errors. And I did this simulation now for the GKP states, where the orange line shows the case where I do trivial gate teleportation in one round, and for the rest of the m-1 round, I'm stabilizing my state because I wouldn't leave it idle. I would have to keep stabilizing it. I'm comparing this with the piecewise error-corrected gate teleportation circuit, where the x-axis represents how many pieces I've broken the circuit down into. And you can see here also my infidelity keeps on decreasing all the way up to 12 rounds. And this is about the number of rounds you stabilize your GKP circuit for as well. So you could actually use this for gate teleportation for the GKP states. So now, to summarize, what I've shown you is a non-abelian QSP framework, which helps you access your Gaussian wave packets in your as your oscillator states with your two-level ancillas while dealing with the Gaussian uncertainties. Using that, I extracted a measurement-free gate teleportation scheme for GKP states, which protects against photon loss. And this protection led to a piecewise approach to mitigate ancillar dephasing, which, in conclusion, gives me a way to teleport gates to the GKP qubits fault-tolerantly using biased noise ancilla. Thanks.
Maybe you have time for one or two questions.
Very nice talk. So how much does this protocol that you specified rely on the squeezing in position being the same as the squeezing in momentum? And if it does rely on that, can you modify it so that it's more general?
Oh, it doesn't. I can vary it accordingly.
Okay. All right. Thanks.
Over here, the right. You mentioned at some point that this also helps with state prep, but then didn't have to go into it.
Yeah, because I didn't have time to discuss it, but yeah. Okay.
But just quickly, is that like, because I know state prep to me is one of the bigger concerns with these bosonic codes. Mm-hmm. Are you planning to do a sort of like a projective preparation? Is that like the idea, or is there a bit more to it?
No, actually, it's rather more general. I use this entangling, I can use this unentangling gadget to prepare cat states, and then I just repeat that circuit to prepare GKP states with a binomial distribution rather than a Gaussian distribution. And so for each delta, you have a specific number of repetitions that works exactly well to achieve the Gaussian distribution. And you can also, in fact, do some error checks in between.
question?
Hi, thanks for the nice talk. I'm a little confused with the error-corrected gate teleportation. I don't see where entropy could be removed there. Could you explain more on that?
Okay. Yeah.
Like, you don't have a measurement or reset, so...
Right. So this gate, this circuit that you saw here, it's the stabilization circuit. That's what I used for the measurement gate teleportation. I basically
Sorry, which one I should look at?
the second one, the one with 4 gates.
Okay. Yeah.
So this is the stabilization circuit for GKP states. It's an autonomous error correction process. I don't need to measure. I just keep resetting the circuit. Autonomously corrects errors on your states. And this is something available for bosonic systems. You could do this for surface codes. It's rather harder to do autonomous error correction for surface codes and basically discrete qubit systems.
But it's unitary, no?
Yeah.
So like how...
But I'm resetting the qubit, so it's like taking a partial trace of your on your system.
Okay. I didn't see the reset there. So
Okay.
yeah, thank you.
Yeah, so the measurement actually is the reset, sorry. The measurement sign at the end of the qubit G wire, that's the reset. That's where I keep resetting the qubit. I don't use that measurement to do anything, ever.
I see.
Let's thank Shraddha and all the speakers.
Thanks.
And we are back in 30 minutes.